In this video, we will start our survey of modern programmable logic devices, beginning with CPLDs from Xilinx. We will use the programmable logic device selection criteria we established earlier to evaluate these devices. To reiterate, there are 11 criteria. Size or logic density, which is the amount of logic in system gates or LEs or slices or ALMs. Cost per logic gate. Speed, which is the maximum clock frequency. Power consumption, static and dynamic. Reprogrammability. Cost per I/O or I/O density. Hard IP available on chip, like memory, DSP blocks, transceivers, etc. Deterministic timing, where the timing is consistent in every implementation. Reliability, which can be measured by the fit rate. Endurance, which is the number of programming cycles and years of retention. Design and data security. Here's the Xilinx XC9500XL CPLD family datasheet, which you can find on the xilinx.com website. Why do you look at the datasheet? Generally, we are trying to determine if we can use this part in our design by looking at its specified performance characteristics. I'd like to highlight some of the significant characteristics of this device that relate directly to our selection criteria. Deterministic timing, 5 nanosecond pin-to-pin delay, 5-volt I/O. Say that with gusto. These parts are used as voltage translators, especially in automotive applications where much legacy equipment still runs on 5 volts. I myself have used an XC9572XL in the design of an industrial product for this very reason. This is a device with flash cells for routing. It is reprogrammable. 20 years data retention is good, as is 10,000 programming cycles endurance. Note the limit in the amount of logic: 288 macro cells, 6,400 gates, 288 flip-flops. The speed is also limited to 208 megahertz. This device has up to 192 I/O pins, so lots of I/O per register, almost 1-to-1. This is an I/O-rich device, unlike an FPGA, which would be register-rich and I/O scarce. Here's an overall top-level view of the architecture. Up to 288 macro cells are connected through the routing matrix to the I/O. The next figure shows a more detailed view of the macro cell architecture. The macro cell can AND up to 54 signals, and then OR together 5 of these plus 5 from an adjacent macro cell, which may itself have an additional number for other macro cells. Choice of clock, enables, resets, etc. are programmable. They're either local or global. The macro cell has only 2 outputs to the I/O blocks. Here's the Xilinx Coolrunner 2 CPLD family datasheet. Here are some of the significant characteristics of this device that relate directly to our selection criteria. This part was designed with low power in mind, hence the name, and includes several low power features. Note the limit in the amount of logic: 512 macro cells, 512 flip-flops. This device has up to 270 I/O pins, so lots of I/O per register, almost 1-to-2. This is an I/O-rich device as well. It has deterministic timing, 5 nanosecond pin-to-pin delay. The speed's limited to 323 megahertz. It's faster for smaller parts. Why do you suppose this is? The parts with more macro cells will have more routing, more capacitance, and therefore slower speeds. This is an example of the scaling problems inherent in CPLDs. This is a device with non-volatile configuration memory that is transferred to SRAM cells for routing. It is reprogrammable. 20 years data retention is good, as is 1,000 programming cycles endurance. Here's an overall top-level view of the architecture. Up to 512 macro cells are connected through the Advanced Interconnect Matrix, or AIM. with each function block connected to the I/O. The next figure shows a more detailed view of the Cool Runner 2 macrocell architecture, which is very similar to the XC9500XL. The macrocell can AND up to 40 signals and then OR together 5 of these. Feed forward from other macrocells is through the AND array. Choice of clock, enables, resets, etc. are programmable, either local or global. The macrocell has only one output to the I/O blocks. Remember the 4-bit comparator? How wide of a comparator can you build with one macrocell? In theory, since 5 signals are combined, each macrocell could generate 5 bits of comparator, a fairly efficient use of available logic. From this, one could also conclude that the implementation of address decoders will be efficient. How many full adders can be made in a macrocell? Just one, as there is only one output. If the XOR output is used for the sum out, then the carry out can be routed to the next macrocell just as the carry in comes from the previous one. However, this only uses about 9 gates in one macrocell, which isn't very efficient. Likewise, when implementing a shift register, only the register in each macrocell is used, so the big PLA structures are superfluous. In this video, we have learned Xilinx offers 2 CPLD families, the XC9500XL and the Cool Runner 2. Both are reprogrammable with deterministic timing and rich in I/O, but are limited in speed and logic density. The XC9500XL family has 5-volt tolerant I/O, which can be important in industrial and automotive applications. The Cool Runner 2 is a lower power CPLD family. Xilinx CPLDs are efficient in the implementation of comparators and decoders, but not efficient in the implementation of adders or shift registers.